Hello, this is Sadashiv Fadnis, Product Marketing Manager for Rubidium signal generators here at Anritsu. In this video, I will be talking about making scalar amplitude response measurements using Rubidium signal generator and Anritsu's MA24340A CW USB power sensor. Rubidium's analog sweep capability, along with sweep synchronization outputs generated, can be used to make amplitude response measurements of active and passive devices. This video will discuss in detail how to set up and measure the amplitude response of a bandpass filter centered around 1.85 GHz with a 200 MHz passband. Here is the measurement setup. RF output of Rubidium signal generator is connected to device under test, or DUT, which is a bandpass filter centered at 1.85 GHz. The output of DUT is connected to RF input of MA24340A USB power sensor. Rubidium's horizontal out is connected to channel 1 and the retrace blanking output to channel 2 of an oscilloscope initially, so that we can observe the synchronization between the two signals. We will then connect Rubidium's retrace blanking output to power sensor's external trigger input port to perform the amplitude response measurement. Note that horizontal output and retrace blanking signals are available on the back panel of Rubidium. Horizontal output is available on a BNC connector, and retrace blanking output is available on pin 6 of auxiliary 2 connector. Retrace blanking output provides a plus 5 volt signal coincident with sweep retrace. The Ethernet ports of Rubidium and oscilloscope are connected to a PC through an Ethernet switch. The power sensor's USB port is also connected to the PC. This enables me to run remote GUIs for each instrument on the PC so that I can control and configure Rubidium and display waveforms of oscilloscope as well as of USB power sensor. This is the PC screen with the 3 remote GUIs. This is Rubidium remote GUI. It pretty much mirrors the GUI on the front panel of Rubidium. This is MA24340A Power Expert remote GUI. With these two GUIs, we have full capability to configure settings on each of the instrument. This is the oscilloscope GUI. The oscilloscope has a VXI11 server, and a snapshot of oscilloscope's display is published on a page every 10 milliseconds or so. This GUI on my screen here accesses that page. We are going to access this page whenever we want to see waveforms of Rubidium. Back to Rubidium remote GUI, we'll first set the output level of Rubidium. So the current level is plus 5 dBm. Let me set it to 0 dBm. It's more reasonable. And then we will move on to the sweep main menu and then choose analog sweep, which will bring us to the setup screen of analog sweep. Now remember, our DUT is a bandpass filter centered around 1.85 GHz with a passband of 200 MHz. So let's set up the start point to say 1.7 GHz, and then the stop point to 2 gigahertz so that we can see the pass band of the band pass filter as well as the two band edges, so that this 1.7 gigahertz and 2 gigahertz gives us enough span to see the band pass as well as the band edges of the band pass filter. And then we move on to the trigger. We make sure that the trigger is set to auto, which is internal triggering. Before we enable the analog sweep, there are two more settings that we need to check. So let's go to level main menu, and within that the setup submenu. So within this screen, make sure that the retrace RF is set to off. Then the second setting that we need to check is within the system main menu. Choose the config submenu, and within this make sure that the ramp rest is set to start. There are two choices here, start and stop. Make sure that it is set to start. With that, we are ready to go back to the sweep menu again. Go to the setup screen of the sweep menu. Now let's set up the sweep time. Let me set up the sweep time which is fast enough to make some measurements in real time. So let me choose the sweep time to be, say, 400 milliseconds, which is 0.4 seconds. With that, I think we are ready to enable the analog sweep. So we'll enable the analog sweep. When analog sweep is enabled, Rubidium generates an RF sweep along with a few additional output signals. The horizontal output and retrace blanking are two such signals. Rubidium outputs a voltage that is proportional to instantaneous frequency between start and stop points of the RF sweep. This is called the horizontal output signal. It is a ramp signal with peak of plus 10 volts. Rubidium also outputs a plus 5 volts pulse coincident with the sweep retrace. This, as mentioned before, is the retrace blanking signal. Let's take a look at these two signals on the oscilloscope. I have connected horizontal output to channel 1 of the oscilloscope and retrace blanking to channel 2. Let me take a snapshot of the oscilloscope page now. Okay, here you can see the ramp signal corresponding to the RF sweep being generated. You can also see the retrace blanking pulse at the bottom. The negative edge of the retrace blanking pulse aligns with the end of the sweep retrace and the start of the next sweep. The ramp signal itself is 400 milliseconds, and I have set up two markers here, one at the beginning of the ramp signal that also aligns with the negative edge of the retrace blanking, and the second marker at the end of the ramp signal, and the delta between these two markers is 396 milliseconds, which is a bit shy, just a little bit shy of the sweep time that we had set on Rubidium, which is 0.4 seconds or 400 milliseconds. So the ramp signifies the sweep time of the analog sweep. And you can also see that there is a short horizontal period at the top of the ramp, which indicates that RF dwells here for some time before starting the next retrace. We are going to use the negative going edge of the retrace blanking pulse as a trigger signal to the USB power sensor, the MA24340A power sensor. Output power from DUT, which is the bandpass filter in our case, is measured by the sensor with every trigger and is displayed in scope mode. Power sensor in scope mode should then show the amplitude response of our bandpass filter. This is going to be our measurement process. Let me connect the retrace blanking signal to the trigger input of the power sensor, and then we can go over to the power sensor GUI to set up the amplitude response measurement in scope mode. Okay, so I have connected the retrace blanking signal to the trigger input. So if I take another snapshot of the scope, the retrace blanking signal is gone because I have connected it to the trigger input of USB power sensor. As mentioned earlier, while describing the setup, Rubidium's RF output is connected to the DUT, which is our bandpass filter centered around 1.85 gigahertz. The output of bandpass filter is connected to the USB power sensor's RF input. We will now configure Power Expert GUI of the power sensor to make the amplitude response measurement. So this is the continuous screen of the Power Expert GUI, but what we want to do is to operate it in the scope mode. So let's configure the scope mode. In the scope mode, you first configure the capture time, and as I had mentioned before, the sweep time of the analog RF sweep is 400 milliseconds. So we are going to capture 400 milliseconds after the trigger comes in, which is at the start of the sweep, right? The trigger comes in at the start of the sweep, and from that point onwards, we are going to measure power for 400 milliseconds, and we are going to do the same thing over and over again with every trigger, which is the retrace blanking pulse. The data points, I think we can leave it at 200 or make it more finer, so maybe I'll make it 400 data points within this 400 milliseconds capture time. We are not going to do any averaging because we are interested in real-time measurement. The trigger, our trigger source is external, it's not internal or continuous, so let's set it to external. Arm type is auto. We don't want any single or any finite number of measurements. We want automatic, which means for every trigger input that's coming, the power sensor should make a measurement for 400 milliseconds from that trigger, right? And then the edge of the trigger is negative, as I had mentioned earlier. And if you go back to the scope again, the start of the ramp was aligned with the negative edge of the retrace blankings, and retrace blanking is what we are using to trigger the power sensor in scope mode. So we are going to set the edge to negative. So first, and I think this is all the configuration that we need. So let me first apply the settings here, and then let me arm the trigger. And here you see basically the amplitude response of the band pass filter. This is the pass band, and then the two band edges. This is on the lower side and this is on the higher side band edges until you hit a a level of minus 50 dBm. And remember, we have set the output power to, let's go back to the Rubidium signal generator screen, GUI. We have set the output power to 0 dBm, and with 0 dBm you have some loss here, maybe 2 or 3 dB loss, and then the stop band is almost 50, maybe 55, 56 dB. This is the dynamic range you are getting in this measurement, and you could get much higher dynamic range if you increase the input power. So let me increase the input power to something like 10 dBm, and then you can see much higher, you should see much higher dynamic range. And here you go. So there is some loss, 2 or 3 dB loss. I think it's measuring around 7 dB here. And then your stop band is around the same point, right? 53 dB, and then 7 dB. So 7 and 53, 60 dB dynamic range. You could get even higher by going higher in power. So you might get all the way up to 70 dB of dynamic range here with this measurement. So we can do actually a power measurement within the pass band. So let me set up the gate and the fence to make that measurement. So let's put the gate start at maybe 80, which falls within the pass band. So let me put gate start at 80 milliseconds, and maybe we can put the stop at around 280 or 290, which is almost the end of the pass band. So let me make that as 290, and then apply these two settings. You should see, okay, so you can see the gate start and the gate stop and the power measured within that, which is about 8 dBm, right? And the output power that we have set on Rubidium is plus 10 dBm, so there is 2 dB overall loss. That's due to the cable between the Rubidium RF output and the DUT input, which is the band pass filter input. And then the filter itself has got some loss. So put together, I think there is 2 dB loss between them, and you can see the pass band output power measurement of 8 dBm. Right. Now, if you want to see what happens at the stop band, what happens in the stop band on the lower side, we can go back to our sweep limits and we can change the start to something lower, right? So maybe I can set it to 1.2 gigahertz and see what the stop band on the lower side looks like, right? And let me look at the power expert in scope mode again, and this is your stop band right on the lower side, and you can readjust let me readjust the gate start and stop again to make the power measurement within the pass band. So let's set the gate start to somewhere around 280 milliseconds and stop to maybe 340 or 330. So 280 milliseconds. Let me do that. 280, and this one is 340. Apply the above settings, and you should get another snapshot. And there you go, around 8 dB, right, within the passband. 8 dBm within the passband. So this is how you can make amplitude response measurements with analog sweep in Rubidium. Let's look at what is happening here at the higher end of the stop band, and you see a small spike here. So it's showing you a very concentrated RF output power at this point. And if you recall, if you go back to my scope snapshot, if you recall, I had talked about a brief horizontal period in the sweep signal, which is where the RF output rests a bit before starting its retrace, right? And because of this rest, you see this spike in the stop band. It's not part of the band pass response. It's because of this brief resting period at the output of the sweep, at the end of the sweep, I mean. Okay, so this is how you make amplitude response measurement, which is essentially a scalar type of measurement using Rubidium analog sweep and also Anritsu USB power sensor, the CW power sensor, MA 34 or MA MA 24340A power sensor. Okay, so in a typical amplitude response measurement, usually your horizontal scale is in frequency, but in our case here the horizontal scale is in time. You're starting at 0 milliseconds and you're ending at 400 milliseconds. So how does this scale, this time scale, this horizontal time scale translate to frequency? So in order to determine that, let's go back to our sweep settings on Rubidium. So we had set the start to 1.2 gigahertz and stop to 2 gigahertz. And as you recall, on the scope, a snapshot on the scope, the ramp is a very linear, the sweep is a very linear progression from start to stop. You can see that by the ramp signal here. If you look at the horizontal time scale here, the scale here maps linearly to the start and stop frequencies, between start and stop frequencies. So essentially your 0 millisecond corresponds to 1.2 gigahertz and your 400 milliseconds corresponds to 2 gigahertz. Now let me do something. Let me modify this to our original setting of 1.7 gigahertz and see how does this translate, right? So again here 0 corresponds to the 1.7 gigahertz and 400 millisecond corresponds to the 2 gigahertz, and you can map the in-between points in a linear fashion. And if we use that to determine the center frequency. I think this is approximately the center frequency of the bandpass filter, which is around, I would say, 190. And if you map to the frequency, it translates to 1.84 gigahertz. That is, if you assume the start at 1.7 and the stop at 2 gigahertz, and then you assume your center is at 190 milliseconds and convert that to frequency, it translates to 1.85 gigahertz, which is the center frequency of our bandpass filter. Now, the question is, how accurate are these scale conversions on the horizontal scale, right? The frequency to time conversions. They are as accurate as the accuracy of our analog sweep. So that is something that users should keep in mind.